Okay, this is exam 3 for Physics 202, Spring 2012. Which of the following statements is true? Newton believed light was a particle because of refraction. That's not true. He believed light was a particle because of reflection. Young showed light was a particle through the double slit experiment. He showed that light was a wave. Huygens believed light was a wave because of reflection. He did believe light was a wave, but because of refraction. So it leaves B. Einstein showed light was a particle through the photoelectric effect. These two mirrors at an angle of 120 degrees. That's this angle right here. Ray of light is 50 degrees on the first mirror. What is the angle of reflection? So if that's 50, this is also 50. It means that this angle is equal to 40. 40 plus 120 is 160. So that means that this must be 20 degrees. There are 180 degrees in a triangle, so 160 plus 20 is equal to 180. So if that's 20, that means this angle is 70. So this angle must also be 70. So the answer is B. Which of the following is true? I like to think of a wave front. In order to bend in this way, it has to travel faster here when it enters the medium N2. That means that N2 is less than N1, so that's C. Your eye consists of a convex lens that creates an image on your retina. You look at a very distant object. Your eye has a particular focal length. In order to focus on a nearby object, how must the focal length of your eye change? So this is your eye. It's a lens. It focuses an image back here. If it's very distant, that means that the light rays are parallel. So they're going to focus at the focal point. So the focal point is the diameter of your eyeball. Now, in order to focus on something nearby, this is your eye, something nearby, your focal point is going to have to be smaller in order to draw your rays here. In order to focus it at the back of the eyeball. So the focal length is going to decrease. That's B. Alright, which of these aberrations occur in mirrors? Spherical aberrations do occur. Geometric and diffraction aberrations, those aren't. That's just made up. Chromatic aberration only occurs in lenses because it's due to refraction. So the answer is 1 only. A. What do you see more of yourself, or what can you do to see more of yourself in a flat mirror? Alright, neither moving away nor towards changes what you see. The only way to see more is to get a bigger mirror. You look in a mirror and see an image of your nose that is bigger than your actual nose. Which of these options correctly give the type of mirror and describe the image? The only mirror that magnifies an image is a concave mirror. Let's see, concave is the only, A is the only option with concave. If it's magnified, in the concave mirror, that means that the object is inside the focal point. So it's also a virtual image, and it's also upright. Remember, I brought that concave mirror to class. In order to see yourself magnified, you had to hold it really close up. It was an upright image, so that also means that it's virtual. Interference occurs in what type of waves? Well, interference occurs in all types of waves, light, mechanical, or sound. So the answer is D. Which statement best describes the phase of these two waves? These two waves are separated or offset by a half wavelength. That's that distance is a half wavelength, so 2. But we can also describe that as being out of phase by 180 degrees. So 2 and 4, that's D for number 12. Two coherent waves have a wavelength of 4 meters. The first wave travels a distance of 3 meters, and the second travels 11 meters. That means that my path length difference is 11 minus 3, or 8 meters. And that's equal to 2 wavelengths. So my path length difference is 2 wavelengths. That means that I'm going to have constructive interference. It's going to be constructive interference. So the answer is A for number 13. Number 14, in a Young's double slit apparatus, by what factor is the distance between adjacent and light dark fringes changed when the separation between the slits is doubled? We need to look at two things. D sine theta equals m lambda. Let's see, what am I doing? I'm doubling this. So that means that this, in order to remain constant, has to decrease by half. So if the wavelength remains constant, my angle theta is going to, or my theta is going to decrease by half. And remember, this is going along with the idea that theta is equal to sine theta is equal to tan theta. That's the small angle approximation. And we, sort of take that into assumption when we're talking about diffraction. So So the sine, if d goes up by 2, sine of theta, which is the same as theta, goes down by a factor of a half. Now, but really I want to know about y, and y is equal to L tan theta. If sine theta goes down by a half, that means that tan theta also goes down by a half. That means that y goes down by a factor of a half. Alright, so let's see, that's D for number 14. After a light from a source passes through two slits, a first order bright spot is seen on the wall at point P. That's this point. Which labeled distance is necessarily equal to the wavelength of the light, A, B, C, or D? This is our path length difference. That at the first order, that has to equal one wavelength. That is your path length difference. So the answer is B for number 15. Oops. Okay, so I have a fiber optic cable consisting of a core surrounded by cladding. Cladding has a lower index of refraction as shown here. I want to know what this angle theta naught must be in order for this to give us total internal reflection. And then is that a minimum or is that a maximum angle? So for total internal reflection, that means that the angle here is equal to 90 degrees. All right, so I'm just going to take this in two steps. I'm going to say N1 sine theta c, that's my critical angle, is equal to N2 sine of 90 degrees. All right, and then I solve N1 is 1.4, N2 is 1.3, and I solve for theta c. And I find that theta c is equal to 68 degrees. All right, 68 degrees. That means, if this is 68 degrees right here, that means that this angle has to be 90 minus 68, which is 22 degrees. And then I solve for theta naught. So I say N naught sine theta naught equals N1 sine of 22. And I solve this for theta naught, taking N naught equal to 1 and N1 equal to 1.4. And I find that this is equal to 32 degrees. Alright, so that's my answer, 32 degrees. There's a second part to the question. Is this the maximum or the minimum angle for total internal reflection to occur? That is, can the angle theta naught be made bigger or smaller and still have total internal reflection? Well, you can only make the angle smaller, because if you make it bigger, show you what happens if you make it bigger. If I make this angle bigger, theta naught, it's going to come along there, and then it's going to come there, but it's not going to have a shallow enough angle, so it's actually going to go out of the cladding. So you can't make it any bigger, so this is the maximum angle. That is the maximum angle. Alright, find the position and magnification of the final image created by the system of lenses, and then there are a series of questions about that image. Alright, so first I just want to find Q1. I know that this is P1 and I have F1, so I solve for Q1. It's equal to 1 over F1 minus 1 over P1. This is from the lens equation to the negative 1. It's pretty simple fractions. I have 1 over 10 minus 1 over 30. The inverse of that, see, that's 3 over 30 minus 1 over 30, that's 2 over 30, so that's 15 centimeters. Let's go ahead and calculate my magnification. It's negative 1/2. Negative 15 over 30, negative 1/2. Alright, so now my image is right here. Right, it's half the original size of the object, so actually a little smaller than I've drawn it, and it's going to be 5 centimeters from the second lens. So that's going to be my P2 is equal to 5 centimeters. Okay, so I'm going to now solve for Q2 in the same way as I did up here, 1 over F2 minus 1 over P2. Negative 1, that's 1 over 15 minus 1 over 5 to the negative 1. Let's see, that is 1 over 15 minus 3 over 15. So it's negative 2 over 15. Negative 15 over 2, which is negative 7.5 centimeters. Alright, so that's my location, or the position of the final image. Alright, now let's go ahead and calculate M2. Negative Q2 over P2. And just putting in those numbers, P2 and Q2, I get 1.5, 3/2, I'll call it. Positive 3/2, because Q2 is negative. And now my total magnification is equal to M1, M2, which is negative 1/2 times positive 3/2. That is negative 3/4. So that's my magnification. Now, is the image real or virtual? Q is negative, so it's virtual. Is the image to the left or right of the second lens? For a similar reason, Q is negative, so it's to the right. Or excuse me, I'm sorry. To the left of the second lens. That means my image is going to be right about here. Oh, excuse me, it's going to be inverted actually. Is the image upright or inverted? The total magnification is negative, so it's inverted. So my final image is right about there. Alright, I have light of wavelength 640 nanometers. Actually, let's see, I changed this so it's not a diffraction grating, but it is a double slit with separation of 667 nanometers. Right, so I'm just going to go and write that here. D is equal to 667 nanometers. The wavelength is 640, 10 to the minus 9 meters. I will go ahead and convert that over into meters. And the interference pattern is projected on a screen 4 meters away. That's my L value. It's equal to 4 meters. I want to know at what angle from the central bright spot is the first fringe. So that's my first order. So D sine theta equals M lambda. I'm going to draw a picture. It always helps me to draw a picture, sort of help you to remember what it is you're looking at. My interference pattern. I'm looking at this one, so I'm looking for this angle theta. Alright, so theta is the inverse sine of M lambda over D. This is M, this is lambda, this is D. If I put that in, I get 74 degrees. Notice that my small angle approximation does not hold in this case because my angle is so big. So theta is 74 degrees, and then I also want to know how far is on the screen is the first fringe. So I want to know this distance, which I'll call y, and this distance is L. Since I know that tan theta is opposite over adjacent, that is tan theta equals y over L. I can solve for y. It's just L times tan theta. That's 4 tan of the angle, which is 74 degrees. And I find that to be 14 meters. So that's number 18. Alright, number 19, convex security mirror has a radius of curvature of 20 centimeters. I know that my focal point is half that, so my focal point is 10 centimeters. And also because this is a convex mirror, it has to be negative. Alright, the convex mirror has a negative focal length. It's positioned so the image of man's body is half times the size of the face, so my magnification is 1/2. Because it's a convex mirror, it's going to be positive 1/2. Alright, it's smaller and upright. It's always upright in a convex mirror. I want to know how far is the mirror from the face. I want to know what is P. So I have two unknowns. That is, I don't know Q and I don't know P, but I have two equations. I can say that M is equal to negative Q over P. Negative Q over P. I'm looking to solve for P, so I'm going to solve this in terms of Q. Q is equal to negative P times M. And then I can take my mirror equation, 1 over F equals 1 over P plus 1 over Q. And I'm going to substitute that in for Q. So I have 1 over F equals 1 over P minus 1 over PM. And then a variety of ways you could do this. I'll factor out a 1 over P. Like that. Solving for P. P is equal to 1 over F over 1 minus 1 over M. Inverse of that. That's equal to 10 centimeters. So that's the final answer. 10 centimeters is the answer. Alright, one more. Grating with 2,000 slits per centimeter is illuminated with a light of wavelength 4,000 nanometers. So first I want to find what is D, 1 over 2,000. That gives me a D in centimeters of 5 times 10 to the minus 4. Which is 5 times 10 to the minus 6 meters. Lambda is 400. 10 to the minus 9 meters. I want to know the highest order number. That means I want to know the order number that gives me theta equals to 90 degrees. So remember, here's our diffraction grating. It has a lot of slits on it. My screen. When this angle theta equals 90 degrees, that means that I can't get any more spots on there because that light is not going to the screen anymore once it gets to 90 degrees. Alright, so I want to solve it for theta equals 90. Sine of 90 is equal to 1. So my equation just goes to D, sine of theta is 1, equals M lambda. Solve for M is D over lambda. And putting this D here and that lambda, I get 12.5. I round this off. Alright, not rounding it up because I can only get 12 orders. Orders are integer values, and just like you can't have a half a person, you can't have a half an order. Alright, so the answer is 12. That was for part A. In a similar way, you can do it for part B. It's just D over lambda. 20,000 slits per centimeter. That gives you 5 times 10 to the minus 7 meters for D. That's just 1 over 20,000, and then you convert it to meters, divided by 400 times 10 to the minus 9. So that's equal to 1.25, which means that you just get one order. Alright, there are the multiple choice answers.